I want to talk about data structures for Fréchet queries and clustering curves under the Fréchet distance. So these are two talks actually, and the first talk might be a little bit longer. So if I run out of time in the first talk, don't worry, I'll go faster in the second talk. So I don't spend too much of your time. And what I want to do is I want to give an overview of current techniques that I use to solve these problems and what's the state of the art. I will be naturally biased towards my own work and work of my co-authors, so please forgive me for that. I hope it's still going to be general enough and interesting to you. And I want to start with the motivation side. So why do we care about analyzing trajectory data, or what is trajectory data? So trajectories appear in many different natural sciences in the form of tracing a signal over time. So this could be naturally the location of a moving object, like for example, you could have migrating animals, or you could have a sports player, a soccer player on the field that you're tracking the location of. Or it could also be more high-dimensional signal, where you have all the positions of the joints of a person who's moving and doing all kinds of movements, and you are tracking this high-dimensional configuration over time. And so this is in like what I would call in an area of behavioral analysis, but you can also think about tracking natural phenomena like hurricanes, or there could be like there's lots and lots of data that tries to capture phenomena of the atmosphere and the ocean, and natural scientists, like geodesists, they try to analyze the Earth system using this data. And obviously what we want to do is we want to find patterns in this data. We want to be able to cluster these patterns in this data and maybe build models and maybe even do some kind of prediction. And for this, we need to be able to cluster trajectories, and we need to also be able to decompose these long trajectories into shorter patterns, really to figure out where do these patterns occur. And so one of the natural important problems that I first want to focus on is proximate near neighbor searching. But let me first set the stage and explain how do we actually measure similarity? How can we measure similarity or distance for these geometric objects, these curves that don't, they don't naturally fit into an LP space or a normed space. So instead, what we do is we look at the Fréchet distance, which I think is a very natural way of measuring similarity of parameterized curves. So yeah, as I said, so trajectory or time series is a sequence of measurements of a moving object, or maybe a signal in general that you trace over time, how it changes. So you get these measurements, and then normally what is being done is you do a piecewise linear interpolation of these measurements, and you obtain a polygonal curve, or piecewise linear curve. You can think of this also as a parameterized curve that, a parameterized curve is just a mapping of a parameterization interval. Let's say we can just fix it to be 0, 1, from 0 to 1 to RD, and RD is the ambient space that the curve lives in. And now it's also natural to look at reparametrizations, which basically just changes how this function, how this interval is mapped to the trace of the curve. So it doesn't change the trace of the curve or the shape of the curve. It just changes kind of how fast we are moving along the curve with this parametrization. And so a very natural way to measure similarity of two curves is to go via all possible reparametrizations and to try to find the two reparametrizations that most closely match the two curves to each other. And this is what the Fréchet distance does. So we optimize over all possible reparametrizations, and then we measure what is the distance as we go along the curve, right? So, so you can think of moving along the two curves with 2 points, and you measure the distance between those 2 points. You take the maximum as you go along those 2 points, and you choose the reparametrizations that minimizes this maximum distance. And so this is not really a natural discrete problem by itself, right? So you're optimizing over an infinite set. Here, this set of bijections, continuous bijections that are increasing. But there are discrete algorithms for this. So in particular, if you want to compute the Fréchet distance between two curves, what you can do is you can look at the Cartesian product of the two parametrizations. So you look at this so basically the unit square. And so any point in this parameterization space corresponds to 1 point on one curve and 1 point on the other curve. And if you want to know if the Fréchet distance is smaller or equal delta, then you want to be inside this free space of points that lie within distance delta, and you are interested in finding a monotone path from the 0, 0 to 1, 1 that stays inside this free space. And the space is naturally decomposed at these vertices of the curves into this grid, and within every grid cell, this free space is convex, and so because of this, we can easily compute whether there exists such a path. So, one way to also think about this, sometimes, or what's sometimes done to explain this, is you think of there's one person walking a dog. So one person is walking on this curve, the dog is walking on the other curve. They have to move forward. They cannot backtrack, but they can individually change their speed, locally change it, and the connection between them is the dog leash, and you're interested in this shortest possible leash that permits such a walk, and this walk would be then also kind of captured in this monotone path, like what exactly this traversal would be. Okay. Now what people do is, okay. So here, we have a path. If I choose delta to be like this, for example, but it's not monotone in both coordinates. It has to go through this, this little edge here. It has to go down. If I make the delta a little bigger, the radius, then I get a monotone path, and this would be the Fréchet distance. This would be my distance of between the two curves. A nice property of the Fréchet distance is that it's symmetric, and so it has metric properties, and so we can work with this. Another version that is often studied is the discrete version of the Fréchet distance. And let me explain it first from scratch, and then tell you what's the connection between the two. So here we're not really looking at the continuous curve, but we're just looking at point sequences. And we're interested in a traversal that has the property. So it's just a sequence of tuples, and the first tuple has to be 1, 1, and the last one has to be the last. M1 and M2 is the length of the two sequences, and in between, from one tuple to the next, you can either move by 1 on one curve or by 1 on the other curve, or you move by 1 step on both of these curves, and then you minimize over all possible traversals, and in each traversal you measure the maximum distance along the traversal, and this can be solved by dynamic programming. Looking at this so-called free space matrix, where you're interested in, is there a path, a monotone path that only uses these 1 entries of the matrix, which denote the pairs of tuples that are within distance delta. And so what's the connection? Well, the discrete Fréchet distance converges to the continuous Fréchet distance in the limit if you subsample a continuous curve. Okay, so here I say P and Q to the M. So this is a sequence that I sample along a curve, and if I take enough of those points, then the discrete Fréchet distance will be equal to the continuous Fréchet distance. And this is the connection. And if you want to think of it in terms of approximation, then you will get, you can also think of it, okay, it approximates it, but then you will get the length, so length of an edge so there'll be an additive approximation in the longest edge or something like this. Okay, so this is more a natural discrete version that sometimes makes it easier to solve problems. And what we do is we look at both versions and we try to transfer techniques from one version to the other version. And what I will focus on first is the discrete Fréchet distance and approximate near neighbors search for the discrete Fréchet distance. And then I will tell you which of these techniques transfer to the continuous version. Okay? Oh, so if there are any questions, please interrupt me. Yes?
Yeah. So does anybody ever look at like the summation version of this?
Yes, so if you put a sum here instead of the maximum.
Yeah.
Yeah. So this is also widely used in data mining, and it's in speech and also other areas. It's called dynamic time warping, but it's not a metric. This is a metric, but the dynamic time warping is not a metric. So it makes it a bit, and that's also something we study, but sometimes it's harder to analyze actually. Okay, so what do we look at? We first want to look at the very basic, fundamental problem in data analysis, which is approximate near neighbor searching. And this has been also a topic in the previous talk, so I think I don't have to really go at length into the definition. Basically, you have a set of points in the metric space, and you want to pre-process them so that when you come with a new point, you want to return a point that is nearby, and this is nearby is defined by a radius that is known at pre-processing time. So this is why we're looking at the near neighbor searching. And you're allowed a little bit of an approximation by a factor of c, so you can return a point that lies within distance cr, or you can say it's there's no point if this radius r is empty, then you're allowed to say there's no point. And this problem, if you have a data structure for this problem, then you can also solve the approximate nearest neighbor problem, which with little extra overhead. Another problem that is closely related and is more studied in computational geometry is the range searching problem, or range reporting problem. There, you are basically you're starting off from a range space, which is a set system. So you have a ground set X and a set R, which is a set of subsets of X. So you could, for example, here look at the set of metric balls. Those are your ranges. And now the task is to pre-process a set of points from your ground set to answer queries for the intersection of a range with your input data. And there are approximate versions of this. You can add like a Minkowski sum with like a metric ball and make it a little bit larger, and then you're allowed to return a bit more. But I'm not actually going to talk about the approximate version. I'm actually going to focus on the exact version. And other variants of this problem that will show up in my talk is orthogonal range searching. This is where this set is a set of hyperrectangles, or all possible hyperrectangles, and semi-algebraic range searching. This is where this set system is, the ranges are Boolean combinations of zero sets of polynomials. Okay, and we'll see how these two things can be used to solve this problem for Fréchet metric. Okay, what's the difference here then in the searching and reporting? So reporting is this where you have to return everything that's in the range, and searching you're supposed to compute, say, a statistic, maybe the number or maybe one element from the set, and that's a bit easier. You don't because this obviously the query will be dominated sometimes by the volume of the range that you're returning, which it's not always what you want to do, but it makes it sometimes easier to actually find lower bounds. Okay? That's why I'm also discussing now. Any questions about this? So this will be, so we're going to work with these definitions now. Okay. Okay, so what's known for the discrete Fréchet distance? We have, so there has been a lot of work on this, and there has been like earlier work that I'm not mentioning here. And there's work for specialized variants where you maybe you only look at certain types of queries or so. So this is not the complete picture, but because I want to be just focused on the main techniques, I'm just going to be focused on these two results here. And I want to explain to you basically the techniques that I used for these two results, and also how these techniques show up in solving the continuous version. Okay, okay, so the input is a set of polygonal curves, each n curves with m vertices each, and they are in dimension d. And here we'll see the dimension is kind of dominated, the dimension of the problem, whatever this exactly is going to be, or how to define it, will be somehow determined by m and d. Okay. And the queries, they don't have to be of like dimension k, m, d. They can also, you could say at query time, okay, I only want to support queries of length k at most. Okay? And then you get a little bit of an asymmetry there, but it's also kind of natural to look at this version. Okay, so for exact near neighbor searching, and actually what we're solving is the range reporting problem. There is this result here that uses space, near linear space, except it has exponential dependency on m, the input complexity, the complexity of the input curves, and whereas relatively high query time, but n to the 1 minus 1 over d plus times some log factors. But we'll see that this is actually tight for range reporting. So you cannot do better for exact range reporting, and at least in dimension 2. And then the approximate version, so if you are interested in just returning a 1 plus epsilon approximate near neighbor, then you can do much better. So you have n times 1 over epsilon to the dk. So here, importantly, k, if you think of k of being maybe smaller than m, this can be much better, but still it's also exponential in k, and the query time is much faster. Yeah? So if d and k is constant or fixed constant, then it's just constant. Okay, so the first result uses semi-algebraic range searching. And by lack of a better name, I just call it semi-algebraic approach. And the second one uses epsilon grids and like a good discretization, and then using kind of exhaustive enumeration in this discretization. And the lower bound, so we don't really have a lower bound for this, I think, but for the range reporting lower bound, we can show a space query time trade-off lower bound, which says, okay, if the query time is q of n, then the space has to be at least this. So it looks kind of big and scary and complicated, but if you plug in this query time here, then you'll see that this space is actually for d equals 2 is optimal, I think. Now, okay, I want to talk about these things, and then we'll also look at the continuous version. Okay, let's start with a discrete discretization approach. So here, what we do is we pre-process each input curve, and we generate a set of candidates, which could be queries that would have this point as a near neighbor. And we want to generate an exhaustive set of candidates so that we hit all of possible queries. Okay? And how can we do this? We want to be dependent on the query time, the query complexity k. So what we do is we compute a so-called k simplification of the input curve, and we do this for every input curve, just separately. A k simplification is a sequence of points, a sequence of k points that has smallest Fréchet distance to my input curve, and you can use dynamic programming to compute this. And I mean, there are different versions of this, so yeah, but so any kind of case simplification should work here. Then we put just Euclidean balls around the vertices of this case simplification, and the radius will be some constant times r. And then you put an epsilon grid on the, or basically you look at a canonical grid, which has a grid length like epsilon r, and you intersect it with these balls. So you get these points inside these balls, and now basically you generate all possible curves that lie in, that use these vertices that all have Fréchet distance at most 1 plus epsilon r. And if you do the math, the combinatorics, then you will see that this number is bounded by 1 over epsilon to the dk. Yeah, so you have one term here is the number of traversals between two curves of complexity k, and yes, and you can also compute this in this time because you look at all possible traversals, and then you go from ball to ball, and within each ball you have 1 over epsilon to the dk many points. Okay. So in total, for each input curve, you store 1 over epsilon to the dk many candidates. Then you just store them in lookup table. Basically, you store all the curves with their near neighbor. And then when you get a query, you snap it to the grid. And then you just look up the answer in the table. So you get fast query time. OK, so yeah, here you have the query. You snap it to the grid. And then you just look it up in the table. OK, now the other approach, the first one in the table, is works for range reporting. But you can also use it for returning one point from the query. Okay, and what we do is we want to use semi-algebraic range searching, which can be solved using multi-level partition trees with a polynomial partition theorem. I will not go into the details of how this works, so this would be beyond the scope, but what you have to, so I'm just going to tell you how to use it. Basically, what we put into the partition, so the partition tree is, so the data structure as a tree, and that every node you store a secondary data structure that is built over all the elements that are in the subtree starting at this node. And then you can continue this and get multiple levels. Okay. And what we'll do is our primary data structure here will be used for semi-algebraic range searching over a set of points, P1, which are, let me go back, which are all the starting points. And then in the secondary, we take all the second points of the curves, and then the next level, all the third, etc. We can make sure all the input curves have the same length just by duplicating the last point. It doesn't change the Fréchet distance. So we store them in this data structure for semi-algebraic range searching, and now what we can do is we can now ask this data structure, okay, give me all the tuples that lie inside this semi-algebraic range. And now we want to use this for answering Fréchet queries, and we have to do a lot of work at query time. So at query time, we get a curve. And this is our query curve. We build an arrangement of disks of radius r centered on these vertices of the query. And this arrangement now has these cells, okay, where, and so the arrangement of disks partitions the space into these cells. And I can, so what's the property of each cell? So if I take, for example, this cell, then any point in the cell has the same distance vector, 0, 1 vector to all the vertices of my query. Yeah? Because I would have to cross one of these boundaries to change a 0 into a 1 or 1 into a 0. So now what I can do, I can fix a free space matrix. And that gives me a sequence of cells. And each of those cells is a Boolean combination of semi-algebraic ranges of disks. So now what I can do is, okay, I can fix one sequence of cells. I fix a free space matrix, and then I go from the beginning. And I take this semi-algebraic range. I say, okay, give me all the curves that have the first point in this cell, the second point in this cell, the third one in this one, the fourth one in this one. And this will be the set of curves that exactly traverses those cells. So this is all the curves in my input that have this free space matrix with my query. And now I repeat this for each possible free space matrix that has a feasible traversal and a union all of the results. And it also gives me a partition. It's a disjoint partition of my query. So I don't have any duplicates in there. And now the space and query time is just for semi-algebraic range searching using these M levels. Okay. So yeah. So as I said, I'm not going to get into like how we get this. This is in the semi-algebraic range searching machinery. Okay. So now we looked at these two techniques. I also promised a lower bound. And so the lower bound is for the range reporting version. And so to get this lower bound for range reporting, what we do is we have to find a difficult set of input and queries. And this lower bound is in the pointer model of computation, where you think of the data structure as a graph and a node. So the graph has a starting vertex, and every node, so there's some of these nodes are output nodes. All they do is output a subset of the input. And a query traverses the graph. So it starts from this starting point, and the query time is the number of steps you have to go in this graph. And now what we analyze is is basically this trade-off of, okay, if I have this query time, if my query time is at most this, what is the size of the graph? What's the number of nodes in the graph, at least? So what we do is we look at an intermediate problem, which is called slab stabbing. So our queries are all points in the unit square. And so this is what we start with in the unit square. And our input are these slabs here, and the query has to return all the slabs that are contained in my query point. So it's a bit of a dual version of what we are looking at, but that doesn't really matter because it's just an intermediate problem. We can reduce our problem. We can reduce this problem to our problem and get the same lower bound. But let's just focus on this problem. How do we get a lower bound for this? So our input will be the groups of k groups of slabs that tile this query space, and they are rotated, okay, to each other. Every point will be covered by k slabs. So the output size will be k, and in the end we will this k is a parameter, and we will set it to our query time. There is this volume argument in a paper by Afshani that says the space for this problem is at least k divided by the maximum volume of the intersection of any two queries, any two input slabs. And in this construction, we can analyze this volume, yes, the size of the query, by looking at like the width and the angle between them. So basically, this volume is like this width times this width divided by the angle, more or less, like up to constant factors. And so we get this as the maximum volume of the intersection of two of these input slabs. And if we plug it in here, we get a space lower bound of n divided by k to the power of 2. That's not quite the bound that we want to get in the end. This is the bound that we know also for simplex range searching, range reporting, actually. So this should be reporting. But we can now extend this to a multi-level version where we have like t dimensions, and we have these slabs in each dimension, and the query is t dimensional or has t to the dimensional, and now we can shrink this volume a little bit by varying the width of these slabs. So we just make sure that for any combination of queries, there will be one of the dimensions will be small, will be narrow, and that shrinks the volume. And okay, so maybe just for intuition, why do we want the volume to be small? The intuition is that if for two queries, the volume of the intersection is large, then the data structure can have one node just for outputting everything that's in that, right? So it can reuse that node for both of these queries. But if there are no two queries where the volume is small, then it needs to have many different output nodes because it needs to handle all of these different queries. So that's a little bit the intuition. And now we can say, okay, we can do the same thing for discrete Fréchet distance. We can kind of emulate these slabs by intersection of two disks. So here, the points that are within discrete Fréchet distance of this line segment, they all have to lie in this intersection of the two disks. And I make my query rectangle, query square small, so that this will be almost like a slab. I can do like this tiling more or less, like up to some approximation. And then I can also combine this in the multi-level way by building longer curves and making these independent, the query things. So yeah, so this is how we get this lower bound. And now, what did I do? Can I do escape or something? No. I pressed some button and made this. Now I have to do Control L or something? Or?
Try F11. No. What is F11? Full screen. I got a Mac for too long.
Presentation mode, maybe? Ah, okay, good. Thank you. Okay. Okay, what's the situation for the continuous Fréchet distance? It doesn't look so good. Okay, so some of this work is very recent. I will focus on the first three. And I will not talk so much about the last two. But let's go through it. This slide will come back. You don't have to memorize these things. So in this work, with Driemel, Nusa, and Charos, we do get also approximation factor of 1/epsilon. This is the ambient dimension. So these are curves that go back and forth on the line. Okay. Yeah, so that's what it is. We don't get these nice bounds for 1/epsilon approximation. We get higher space bound in particular, and also higher query time. But we do get the same bounds as Filzer-Katz paper for 3+epsilon approximation. And then we also have even something in between with linear space. And the techniques used here are, so it uses this discretization approach in combination with something called signatures, which is a very special type of simplification that works in 1D. And I will talk about this in a minute, how this works. And we will also see some conditional lower bounds based on OV that show that basically these, in some sense, these bounds are tight. Then there is, this is also in D=1 for exact range reporting. Again, you can also use it for near neighbor searching. And maybe I should go first to this. So this is basically an extension of what we've just seen, except now our semi-algebraic ranges, they look a bit more complicated. And this is a kind of an adaptation of this to 1D, where my semi-algebraic ranges are just intervals. So it's kind of natural that you kind of go back to orthogonal range searching here. But it's not quite as easy as you may think so. I'll show you an example of what these ranges look like. And very recently, we could only do it up to ambient dimension 2. Of course, yeah, so we care about dimension 2. These are the trajectories I showed in the beginning, but there are also higher dimensional trajectories we may want to be able to process. And we hadn't earlier been able to extend this. This uses some of, in some sense, the semi-algebraic ranges that we formulated, but takes it a bit further and builds these polynomials, and they also work in high dimensions, but this is, of course, it's a prohibitive space and query time. Yes, prohibitive space bound. So it uses point location and arrangement of 0 sets of polynomials. But I won't have time to talk about this in detail. And then there's also a variant of this discretization approach for higher dimensions, but it has a dependency on some kind of spread assumption, which is not exactly the spread of the vertices. This also contains some distance of vertices to edges. It's it's also relatively complicated, but it uses a kind of an embedding into a doubling space. So this is kind of the idea of this approach. But so the main drawback is that you have this dependency on very weird dependencies with the current techniques on the spread. Okay, so let's go first take a step back and think about what's really the problem, what's the challenge here. And I think the doubling dimension kind of maybe gives some argument of why the problem is more difficult for the continuous case. So we've seen doubling dimension also in previous talks. So in the metric space, the doubling constant is the minimum number such that any ball radius R is contained in the union of at most T balls of radius R over 2, and the doubling dimension is a log of that. Okay, so think of how do you cover a ball with balls of half the size. That gives you kind of an idea of kind of the volume in this space. It's called doubling dimension. For discrete Fréchet distance, the doubling dimension is roughly d times m, which is ambient dimension times the complexity of the curves. Okay, so you can prove this by just if you are for example, so I mean you can use this construction and then extend it using the coordinates that you have. But for continuous Fréchet distance, the doubling dimension is unbounded. Obviously, so if you have many vertices, that also goes up. But so if you fix the complexity of the curves and the dimension, the doubling dimension will be unbounded, and it's kind of a weird construction. But basically, even in d equals 1, so these are curves that go back and forth on the line, and with m equals 3, so they have, or maybe this should be 4. I don't know if it was the number of edges or vertices. So here it's the number of vertices, so maybe it should be 4. These go back, and each of these curves has a zigzag, and they all have the same width. We place them shifted against each other so that all the pairwise distances are exactly r. And if you want to cover 2 of those with a ball of radius r over 2, you would need basically a higher complexity here. And you need to be able to do 2 zigzags, but the center is not allowed to do this because we fixed the complexity. So this is a bit, so somehow you think, it should not be really that the doubling dimension is unbounded, but that's just what it is. So, okay, so I already alluded to that that we can use this discretization approach in 1D, but we use this special type of simplification, which are called signatures. So here we have a one-dimensional curve, A, this thing, and I draw it like a function graph. So it just goes back and forth on the line, but to be able to see what the curve does before, we draw it like a function graph. Okay. This delta signature has the following property. It's a so it contains the starting point and the end point, and then in between it contains an alternating sequence of maxima and minima that have a large distance to each other. So, so the first starting end is a bit different, but all the interior points, so two consecutive interior points, they have distance at least 2 delta, and they come from the original curve. And all the edges that are contracted, they have length at most 2 delta. So, yeah, so it kind of this delta signature gives me the important minimum and maxima for a certain scale delta. Yeah, and this is under some general position assumptions. This is also unique, and it kind of serves in some way like maybe like a kind of canonization, and it will help us to generate these candidates so that when I get a query, I can snap it to a candidate. Okay. So the signatures have very nice properties. In particular, if I have a curve B, like another curve, that has Fréchet distance at most delta to my curve, then it must traverse this area, these intervals, or these delta balls around the signature vertices in the right order. And also, if I take the 2 delta signature of this other curve, then all my vertices of this 2 delta signature, they have to visit these ranges in the right order. And so I'm not proving this here. It's but this is this is a nice property of these signatures that helps us to use the discretization approach. And right, so what I will look at is the 3 plus epsilon, which is the easiest approach, kind of a straightforward adaptation. So what we do for each input curve, we compute the R signature, we discretize these O of R ranges, then we generate all possible K tuples that traverse these ranges, these balls around the signature vertices, and I generate all K tuples that lie within Fréchet distance 3 plus epsilon R, and I store them in my lookup table. Then when I get a query, I compute the 2R signature of the query, and I snap those vertices to the grid. And then I look up my answer in the table. And just by triangular inequality, you get an approximation factor of 5 plus epsilon. If you do a more careful analysis, you can show that this gives you, this approach gives you an approximation factor of 3 plus epsilon. And we get these the same bounces in the discrete case. Yeah?
Why do you have to generate tuples with 3 plus epsilon times R? Why can't I use like 2 plus epsilon times R?
So why can we not do 2 plus epsilon? So we will see that it's, so maybe we're actually doing 2 plus, so this was the original approach that we did in this other paper. And then in the paper with Brinkmann, Nussbaum, Psaros, we modified this a little bit. So I'm not exactly sure if we did use 3 or 2 here. I'm not exactly sure, but definitely you need to go a bit larger to capture everything. Yeah, so I can look it up and then maybe follow up later. Okay, now the lower bound. Okay, so there's some more. Maybe I can go back to this. So there's some others. Here, we cannot use signatures. We use kind of an extension in the beginning of the end. We store more maxima and minima, and then in the end, it could be that we have m vertices that you have to put these ranges on, and then that's why you get this higher space bound. And we also have to generate candidates at query time. There's no easy way of snapping that gives you exactly the point in the table, but we have to basically generate candidates both at input, at preprocessing time and at query time, and then we see then is an intersection. If it's not an empty intersection, then we have a near neighbor. And the other, the thing in between, there we managed to do all the candidate generation at query time. So that's why we get the linear space. Okay. And there is a conditional lower bound based on orthogonal vectors. So also this is something you've seen in one of the previous talks. Orthogonal vectors hypothesis, so I think I don't have to, I can probably be brief about this. I have, here we have this binary version. We have two sets, A and B, of vectors of dimension D, binary vectors, and the dimension D is, think of it as like log n or more. And you want to know, is there a pair of vectors that are orthogonal? And the orthogonal vectors hypothesis tells you that there's no subquadratic algorithm for this. And there's a, so the strong exponential time hypothesis implies this, but it's also a hypothesis that kind of stands on its own. So people somewhat kind of believe in this and do reductions from it. Here, how do we apply this? We look at the offline approximate nearest neighbor, near neighbor problem actually. We preprocess n curves for alpha approximate near neighbor queries, and then we run n queries. And we look at the total time that it takes to preprocess this and to do these queries. And we say, okay, if I can do this using a data structure for this problem, I can solve orthogonal vectors. Okay? And basically, so we go via the unbalanced version where the two sets are not quite the same size. So the one set is smaller by a factor alpha, or yeah, so one is one size. The set is alpha times the other. And why do we do this? Is because we want to lose some dependency on the preprocessing time. If we make our sets that we have to preprocess smaller, then the dependency on preprocessing kind of is not dominating everything. So then it becomes more interesting. And then also we go by another problem called one-sided sparse OB problem, where one of the two sets, so the vectors, they can only contain few ones. And then that gives us a better dependency on the complexity k of the query. But I haven't put all the details here. Basically, I mean, the reduction is really easy. It's much easier. So there is an OV reduction for computing the Fréchet distance, which is relatively complicated. This is much easier because we just use these gadgets. And we say a 0 in a vector of A is just straight. Line. A 1 has this long zigzag. A 0 in set B has this shorter zigzag. And a 1 in a set B is also straight. And now, basically, you have to look at these combinations, right? So what you want is that 0, 1 and 0, 0 are close, and 1, 1 is far. And here, 1, 1, this is the far. They have far distance from each other. So they will not be, so if you have a 1 in the same place, then they will not be orthogonal, and the distance will be far in Fréchet distance. And now you just generate these vectors, and you put them in your data structure, and if there's a near neighbor, then there are two vectors that are orthogonal. It's really not more than that. And we get these bounds that show, so basically if alpha approximation is between 1 and 2, so we can put, so what we want to show is we want to show tightness. If we set epsilon to some constant, you look at our the data, what do we get from our data structure and preprocessing and running n queries, and then you compare it to the OV bound, and basically, yeah, so for 1 plus epsilon we get this, and then with this reduction we say that anything better than this would be a contradiction to OV hypothesis. So this shows like some tightness here, also in the what does it show? Like this factor m over k to a little of k. So this you have to have some kind of factor like this here, and also from between 2 and 3 we also get in a similar way a tightness of some of these for some of these parameters. And then, let's see. We don't get tightness for this because anything beyond approximation factor 3, you cannot get an OV lower bound with these techniques because of triangle inequality, basically. If you have an approximation factor more than 3, you cannot distinguish anymore between these two points. By triangle inequality, going by the others, they have to be short distance. So then this all breaks down. So we don't have tightness for this one, but it looks relatively good. Okay, so now I guess so. I have a bit more time. So the question is where I should break, but maybe I will go a bit further, and we'll just have the break a bit later, and then the second talk will be a bit shorter. So, okay, let's look at this. Right. So I said for d equals 1, these ranges are kind of like orthogonal, but it's not that easy, because if you think about the problem, you basically you can think about our approach. So we have our input curves, and we just look at them in their natural parameter space, right? So which is here in this case we have let's see. So we look at the query space. So here in this case we look at S1, S2, this is an input curve, and Q, this is my query, and I want to know what does these Q, so any curve with 4 points, what is the shape of the range that lies within Fréchet distance rho to this very simple input curve? And obviously, so Q1 has to be within some distance to S1, Q4 has to be within some distance to S2. Those are just intervals for those 2 dimensions. And here in between something happens, there's some dependency, because the zigzag cannot be too large. Okay, so if they are in the other directions of Q1, Q2 comes first and then Q3, then Q3 is not really a problem. It doesn't really matter where they are. They shouldn't go out too much of this range. But if they are kind of in opposite order, then they cannot be too far from each other. But if they are close enough to each other, then I would still be within this metric wall. And so if you look at Q2 and Q3 here, kind of in this plane, then that kind of looks exactly like this. We have Q2 and Q3, they have to stay within the entire range of the curve. Yeah, so S1, S2 plus rho, and S1 minus rho. And then there's this dependency, which gives me this linear constraint. So this is not an orthogonal range, but we can make it orthogonal by adding extra dimensions. So it's kind of like a lifting trick. Of course, it also gets a bit more complicated when you have longer curves. So this is a very simple example, just to kind of meditate a little bit about what the problem looks like. Okay, so, and it's also in 1D. Now let's look at it more generally. What do we want to do is we want to store information about our input curves in our, let's say, semi-algebraic range reporting data structure. So choose these levels in the right way and the points that we put in these levels, so that at query time we can solve the decision problem for the Fréchet distance. And basically we want to know, does exist a monotone path in this free space diagram? And we want to know, what do we need to know from the input curve at query time to be able to make this decision? And well, again, so what we did before is we fixed the traversal, and then we knew where would the path be and what would be the conditions on the path with respect to the coordinates of the input curve. Now we do something similar. We fix a sequence of cells, and now we think about what was the condition on these coordinates so that a monotone path exists. And we can write down these conditions and then turn them into, essentially turn them into polynomials in the end. And so the first two are easy. The predicates, they just say, okay, the input, the first and the last point, they have to be within distance delta. Yeah, so what I wrote down here is for 1D. Okay, so I wrote these conditions down for 1D, but in higher dimensions, they look very similar, these high-level predicates. So we have this endpoint condition. Then we have to be able to get through this cell boundary, that is a vertex edge condition. So this vertex corresponding to this point and this edge corresponding to this edge on this curve, there has to be some point along this edge so that we can get through here. And so there exists a point. Yeah, so this is really for 1D, which is a bit easier, but in 2D they look very similar, such that there exists this points so that, at distance at most delta, or rho. And then we have these monotonicity constraints that say, we can go through these cell boundaries in a way that we still get a monotone path. And those are imposed on all combinations. So if you have like a longer stretch here of vertical or horizontal cells, so in case a horizontal stretch, then these entry points between these cells, they have to be, they cannot like first go up and then go down. And yeah, and then these are these conditions which we impose on all pairs of cells on the one in the one dimension and one cell on the other. And then yeah, so for d equals 1, we can turn these into orthogonal ranges, or we can look at the dual problem and solve it with hyperrectangle stabbing, which gives us a better dependency on the input complexity. So either input complexity or query complexity. If we look at the dual, then we can get better complexity in one or either of the two parameters. For d equals 2, we were able to put these into semi-algebraic ranges, and the difficult one was the monotonicity one. And so there we played some tricks to be able to capture this with these semi-algebraic ranges. But we were not really able to do it in higher dimensions because some square roots or something showed up. But now with this, now there's this other way of looking at it, turns it into polynomials, where in the end you can use some version of this also to solve the problem in higher dimensions, but it then uses this brute force point location in these arrangements of zero sets of polynomials. So this is the other the new paper by Zheng and Huang that I'm not really talking about right now. Okay, so yeah, so we have, maybe we can look at lower bounds. The lower bound, the range reporting lower bound that I showed before, it used this slab stepping and stepping in the multi-level slab stepping problem, and then we said we can solve this problem. We can do the same construction with these intersections of disks or balls to get these slabs. This doesn't work anymore because we're now in a continuous problem, and we don't really have these intersections of disks anymore in our problem. So it's a bit more finicky to work with. But we can still build gadgets to get some things to still emulate the problem. So again, we have these k groups of n over k curves each, so that every point is covered by k ranges. And then the curves, they look like this. So so we have the query is just a line segment that kind of goes from this edge to this. And my input curve that somehow traverses this grid. And I want the curve to be such that it only contains the queries that intersect the this edge here. So I want kind of this kind of funnel here, that contains all the segments that should lie within the range of the input of this input curve. And I can do this by putting a curve here that does this zigzag. Okay, because now my this edge has to pass through the intersection of those two balls, and I can place it such that it's exactly what I want. And now, why does it give me slabs? Well, I can kind of dualize these curves. I can now I dualize the queries and look at these ranges. And so I think what we did is we looked look a very simple parameterization where we looked at the slope and the y-intercept or something, and then we get a dual plane that all possible queries lie in this range, and then one of these curves kind of looks like a slab in this space. Okay, so in the end we can still do the same construction, so we get the same bounds, so this is my basically my summary slide. So we talked about these results, and we didn't really talk about these other two, which they're not now covered. I'm sorry. This is by Sheng and Huang from 24, and this is the other one with my students and postdoc, Jacobus Conradi and Benedikt Kolbe. And we did show some tightness here in this area using range reporting lower bounds and conditional lower bounds based on orthogonal vectors. And those are, I hope, all the references. And that's the end of the talk, my first talk. Thank you.
Questions? So I have a question on the setting of the parameters. So then when you have m large, so you would expect m to be small, like logarithmic basically.
So here in this range reporting, we actually assumed m to be a little of n, yes. Also. But in the but here I think you don't need that actually. M could be long or could be large. Whether you expect m to be, and you mean in practice, whether you expect m to be in log n, it's a good question. It really depends on what your data set you look at. You really need a lot of curves then, because often trajectories are long. So.
But you can always approximate them just by
in a continuous case, you can approximate them well. In a discrete case, then you lose something. Yes. So I will talk a little bit about this in my second talk, because another problem you have is that you don't really know where to cut the trajectories. So what usually happens is you throw some sensors in the ocean and then you track them, and it's rarely the case that there's a clear starting point and a clear end point for the pattern. So there's this one data set we looked at of homing pigeons. They have a clear starting and end point, and there you can cluster them nicely. But usually that's not the case. Also, when you put these sensors on doing motion tracking, or if you put the sensor on a bird that you're tracking that it's migrating, you're happy if you can catch it and put the sensor on, and then it'll just run and collect data until the battery dies. And so you get very long trajectories in practice.
Other questions? Well, thank you. So let's